Okay, doing the EKG lab. You know, this first video is just kind of talking about the stuff I've just been talking about. So it's just another place for you to see somebody talking about what we've been talking about. He's a little probably more animated than me.
What is going on, guys? Don checking in. Welcome to MIT.
Right, so all right. So if you want somebody who's got a little more energy than me, you can check him out. Maybe he'll help you understand the concepts as well. Yeah, he's hilarious, but he does a good job. So normally, if we were in the lab for real, we actually would connect people up to this machine, which records the voltages on your skin and then puts them out on the screen. Like the old school EKG things literally were this analog thing where the voltage on your skin went through a little coil that magnetically moved a little arm that made a little pen move, and there was another strip of paper they called the strip chart recorder. The paper kept rolling along and the little needle would move, driven by the voltages from your skin, and you'd have to count little boxes, how many boxes, because the speed of the strip chart, the paper was such that each box was a certain fraction of a second. So you wanted to see the PR interval, you'd have to count boxes. And you know, the system we have, it records it by a computer. You can use little mouse clicks to actually tell you the timing difference between this and that. So this video that I'm going to show you right now is basically how you connect somebody up to our Power Lab system and record their EKG. And then we'll talk about what you actually are responsible for turning in as part of your lab. This is also when I had a little more time and I was able to play around making really fancy looking title like blocks and stuff. 3D extruded text. So be impressed. All right, so we're gonna start connecting things.
All right, so
Can
maybe the screen.
Yeah.
Physiology.
All right, so then we've got the lab chart running, and now let's see how we hook people up.
Hookup picture of the hookup and the box. All right, removing the jewelry, watch, plug in the bioamp cable into the bioamp socket.
I'm going to show how that actually goes.
Connect the 3 leads to earth, ground, and so maybe if you want to.
And the pulse transducer actually can pick that up. Oh, I should. So this will be for later, not for the EKG. This is for looking at pulses here. Yeah. I'll talk about that in a little bit. All right, let's wire up our subject.
Catching. So then, yeah. So grade.
So here I wrote this here. Like getting a good EKG signal, it really matters that you have a really good connection between the electrodes and the skin. So you usually do some exfoliation, get rid of like the loose skin, as well as cleaning up, make sure there's no oils or dirt or anything. It makes a huge difference in getting a really nice signal. So the preparation before you stick the electrodes on makes a difference. Right? Normally, we could do this to you, but we were recording this right as shutdown started.
All right. So, and then let's make sure they, see that little snappy electrodes.
Yeah.
Right, and yeah, these are nice. So it's got like a little electrode in the kind of gel, and it's got a snap on the top to connect things to. So it's a really nice connection against your skin. Sometimes in school labs, they have these kind of little clips that go across with this goopy, mucky gel, and this is way nicer. This is more what you would do in a real like diagnostic situation. These little electrodes.
Make sure it's really on there. There should be an extra in the matrix here.
Okay, so the white goes on your right arm. Left is black. Green on the right.
And so this is going to allow us to measure the voltages on her skin that are being generated by her
All right,
heart.
so now you're going to relax. And now, let's see, hit start. There's a beautiful EKG.
Very nice.
All right, and we can show how you can like increase or decrease the too big, and so that little plus, come into focus there, there it is, plus minus there on the left side. And then you can also show we can change, instead of 10 to 1, maybe go to 5 to 1 to kind of spread it out a little more.
That's one of the nice things about doing it in this electrical, like kind of digital domain. We're basically converting analog signal into a digital signal, and then it's really easy to manipulate. You can, magnify it, stretch it out, again, measure across it by setting markers, really easy. Some of the old school EKG stuff still is more analog, basically a little pen ziggling up and down on a little piece of paper that's being pulled along by a motor. This is supposed to simulate that, but it's way easier to analyze. Should also take a look. You can see the P, the QRS, and the T. The proportions of the waves will depend on which places you're recording it on the body. Given the way we've set up the electrodes, it's actually normal to have the T wave looking like a bigger mountain over here. There's nothing weird about that. That's what's important, is just noticing P wave is the first bump, QRS is the second complex, T wave is the third one, and then it starts all over again. So we have printouts or PDFs. So part of this lab is going to be printing out Tina's EKG and like annotating it, being able to draw on it and make sure that you're clear about which bump is what and what actual heart cardiac activity it's relating to.
It's kind of pretty. So there we got a beautiful PQRST.
Yeah, we'll keep it at 5 to 1.
Yeah, I think 5 to 1 is good.
Yeah.
All right, so it looks like our subject is healthy.
Okay, so this part you do have to write about in your lab write-up, like what happens when our subject clenches her fist. So she's gonna just, and you'll see what happens, what it does to the electrocardiogram, and you have to think about why it happens.
We see she's relaxed, and we'll get it started. And now, go!
Move your arms.
Move them around. Whoa! And then she's relaxed again, and it's back to normal.
All right.
All right, so what do you think happened there? Did everybody see what did the EKG look like when she was clenching?
It was all over the place.
It was all over the place. And why?
Was it picking up signals from her clenched muscles?
Exactly. Right? Remember, you're just recording the voltage on the skin. And when she's relaxed, the predominant voltage that's coming through is from her cardiac muscle. But when she's clenching, we saw like a skeletal muscle, part of the excitation contraction coupling is depolarization, action potential across the whole sarcolemma. So when she's clenching, all of those muscles are creating crazy voltages that are much closer to the electrodes, are going to swamp anything else coming from the heart. So make sure you describe your observations that you see in the video here and talk about, what it means or why it happens.
So cardiac and skeletal are being shown on that specific one.
Well, I mean, it's just the voltage on your skin.
Okay.
And it's whatever is contributing to that is going to come through. Right? So cardiac muscle has depolarizations, skeletal muscle has depolarizations if it's contracting. Like the heart, basically, unless you're dead, the heart is going to always send out signals every every beat, because that's what's coordinating the heartbeat. Skeletal muscles are only going to be depolarizing if somatic motor neurons are stimulating them to depolarize. So,
Okay.
right, and this, and ultimately your brain is making voltages that theoretically are going to be on your skin, but they're so tiny that they're irrelevant in this. So, but the electrodes are basically measuring the voltage on your skin. That's ultimately what they're doing, and it just happens to be that when you're relaxed, the predominant contribution to that voltage is your heart, depolarization of the cardiac muscle. On this next part, which is again there's one more minute left here. It's basically showing you how to set the markers to measure the distance from the P wave to the QRS. We talked about that internodal pathway giving you a little delay from when the atria depolarize to when the ventricles depolarize. So part of kind of the evaluation here is to make sure that delay is about the right amount of time. So the value measured in this little video is going to be important in your write-up as well. Then in your write-up, it asks, what is that PR delay? Why is it important? You're going to have to kind of make sure you record it from this part.
Okay, and drop it right at the beginning of the P wave.
There.
Oh, no, you can just like right there. You can just put it there.
Right.
Yeah.
Okay.
Let go. And now put the cursor there. You had it
At the
beginning, just at the rising of the QRS there. And now we can take a look up here.
Let me go back real briefly.
Now put the cursor there. You had it
at the
beginning, just at the rising
There it
of.
is. All right. So this is something you don't need to know how to do because you're not actually using this particular system for this lab. But basically, if you put the marker on one spot and then put the cursor on another spot, it will then just tell you what is the time difference between those two, where that marker is and where that little butterfly of that cursor is. So what she's done here is put the marker at the beginning of the P wave. We have the other cursor here, right where the R is going up. So this is basically from when the atria start contracting to when the ventricles start contracting. And we're going to be able to look at that timing difference.
The QRS there. And now we can take a look up here. And we see the delta time is 0.12 seconds, which is total.
Is that worrisome or is that good?
Good.
That's good. Remember, we said somewhere between 0.1 and 0.2 seconds for that delay is about what you want to see. So Tina's heart looks like it's doing well.
Totally normal. Woo!
Yahoo!
All right.
Okay.
All right, so for this part 1 of the lab, down at the bottom of this module, it says, here is the data for you to print out and annotate. So like, where it says like print out your print out your subject's EKG and draw on there. Here it says part 1 EKG PDF. So basically you have this thing that you can print out, and on here you can just draw right on this and show where is a P, where is a QRS, where is the T, and also make sure you write out exactly what it means, right? What is happening, what is generating the voltage that you're seeing on the EKG there. So for part 1, it's basically, and it's also asking you to, show where the PR interval is and draw that on there. So the first part is just kind of getting familiar with an actual EKG and making sure you understand the different parts. And you can get the PDF to print out and put in your lab book write-up. All right, the second part of this is going to add in another measurement, which is going to be your pulse. And basically, it's we have a pulse transducer that you put on your finger that actually measures the movement of your finger. As your blood pumps, your finger actually swells and relaxes and swells and relaxes as the pressure goes up and down between systolic and diastolic. So here's your finger. Here's this pulse transducer that you put on here. And it's actually a little accelerometer. So as your finger swells and goes down, there's an electrical signal that comes off here that is proportional to the motion. It's a mechanotransducer, right? Transforms mechanical movement into an electrical signal. This is my little pulse transducer. And you're going to see kind of this. Basically, as the pulse reaches the finger swells a bit, it goes up, and then it comes back down. This is not an EKG. Right? This is about movement of finger. As the finger swells and relaxes, you're seeing the pulse wave arriving at the finger. I should also mention this is different than the things they use for pulse when you're in a more clinical setting. The little, where are they? I have one here even. Like the little pulse oximeters, which probably most of you probably have these actually right now to check to make sure if you weren't getting COVID or whatever. This is actually shining red light into your finger, and and you can see this is like saying my blood oxygen is at 98% or whatever, and which is good. But so a pulse oximeter that they use like in a hospital situation to measure your pulse is actually looking at like hemoglobin, like absorption of red light and stuff like that, and blood oxygen levels. So it's more, we have these little mechanical pulse transducers just because they're cheap, but they work fine for what we're looking at. And this is basically going to let us see the pulse, right? If you put your hand on your wrist, you feel the pulse. Ooh, ooh, ooh. The pressure is pushing and relaxing and pushing and relaxing. That's what the pulse transducer is measuring. And again, we can have both the EKG and the pulse transducer at the same time, which is what we're gonna do. So when your heart, here's your aorta. We're going to have, in this picture, there's the left subclavian artery coming into the left brachial artery. The left brachial artery then splits into, in fact, we should just give these names because we're going to use them a little later. We're going to go into our radial artery and our ulnar artery, into our little palmar arch, into our digital arteries. And again, we have this little pulse transducer right here telling us what's going on here. So for this next part of lab, part 2, we're going to actually be looking at the speed of the pulse wave. And the basic idea here is the ventricles contract. And that's going to push the blood out. We have like this pressure wave leaving the aorta here, leaving the heart. That pressure wave actually travels at a certain speed. It keeps moving. This is my little pressure wave. This is not an action potential. And eventually it shows up here and we see the pulse arrive at your finger. But it's not going to show up instantaneously. Once the heart pushes or squeezes, that wave has to propagate and move along the vessel before it finally gets to the finger and shows up there. So what we want to do is figure out what is the speed? How fast does that pulse wave travel through the vessels? There is a clinical relevance to this. It's still, it's not something people use so much, but people have done work correlating the speed of the pulse wave with like kind of the stiffness of your blood vessels. Kind of if the blood vessels are stiffer, that tends to go faster. If they have more kind of flexibility and elasticity, it tends to go slower, just due to the mechanical properties of how things propagate like that. But to calculate speed, this is a rate. How do we calculate the rate of anything? This is what we want. What is the speed of the pulse wave? So we want to figure out what is the rate of this pulse wave? What is the formula we use to calculate rates?
Distance over time.
Exactly. It's just distance over time. So the distance is kind of easy. The distance, we're just going to put a tape measure and we're going to measure how far is it from, approximately, because obviously we're not going to have them cut open and measuring exactly on the vessels, but we can approximate by putting the tape measure on their arm and up their chest and figure out what's the distance. To figure out the time, how are we going to figure out the time that it took from when systole started to when the pulse wave arrived at the finger? How are we going to know when systole happened, when the pulse wave actually was generated, when it was started?
Are you going to look at the EKG?
Yeah, and what particular part of the EKG is going to tell us the moment that the heart is actually squeezing to start the pulse wave?
The QRS complex.
Yeah, exactly. Right, because that's correlated with the ventricular systole, the ventricles depolarizing and squeezing. So QRS complex is going to give us a time point when the pulse wave starts. And then on the finger, we can just see the pulse wave arriving as the pulse transducer tells us it's arrived. So with this background, I'm now going to shift and show you just a quick little video of how we measure it. So here, this thing, part 2, estimating the speed of the pulse wave.
All right, so now it's time for the pulse transducer.
Bad influence.
So pulse transducer,
Can't wait till all this goes away.
yeah, let's put that on there and have it nice and firm, but not cut off her circulation.
Okay, so
And-
I'm gonna show a sample.
Yeah, so now start it up again. And there, I'm gonna zoom in on the,
So just to be clear, there's two different signals happening now. The bottom is the EKG, which we've already been working with, the electrical voltage measured on her skin generated by her cardiac muscle depolarization. The top picture is really super different, even though it looks kind of similar and it's, going at the same frequency and rhythm. This is the movement of her finger due to the pulse kind of pushing pressure, increasing and decreasing, and her finger swelling. So it's movement of her finger as it swells and relaxes due to the pulse pressure going up and down.
You want that any bigger?
so just pulse transducer on the top, EKG on the bottom. Even though they look kind of similar, they're actually very different things. All right.
Give a good notch.
Or the dichrotic notch. All right, so now let's stop that. And now let us click and set a marker. Take the marker to the QRS. So ventricular contraction. Perfect. And now let's put the marker to when the pulse is arriving at her finger there. And
Yay. In time.
so there it is. Now I'm moving over to see the time. And it looks like 0.3 seconds.
So you're going to need this data as well for your write-up. So we see that from when the QRS was recorded and the pulse wave started to where the pulse appeared at her finger, it was 0.3 seconds. That's going to be the time. And then again, what's the other thing we're going to need?
Distance.
Pretty nice. Now we gotta see how the distance that the pulse wave went. So 10 centimeters below her jugular notch is where her aorta leaves the heart. And then following the subclavian to the brachial, down to her finger,
There you go. So
and
maybe 5.
Yeah, so again, we had to this was again right after we were going into shelter in place and everything. So normally you would have somebody helping really push it against their body to make sure that you get a more accurate value. But you're going to get a speed that is totally typical. So just use this 105 centimeters as the distance that the blood or the pulse wave had to go through the vessels.
cool. All right.
All right, so that is what you're going to need. What you're going to need for part 2. And again, there is a printout that you can use. In fact, I should show you that printout. If you go down here, part 2, EKG and Pulse.pdf. If you open that puppy up, you have the EKG and the pulse. And again, in your lab write-up, you should show how you use this to actually find that timing. You'll have to show from where to where did you measure that time to actually get the time to measure the to calculate the rate. So that is that. The last part of this lab is just looking at the pulse, and I'm going to redraw that picture of the arm. Again, if you've been in anatomy, you totally know there's the brachial artery coming down your arm. Then it splits towards the thumb as the radial artery, and down towards the pinky as the ulnar artery. Then there's the palmar arch. There's a superficial and deep palmar arch. And then the digital arteries going into your fingers. So it's actually useful to know where these are, both for taking pulses and also for knowing pressure points. So this radial artery near the thumb here, that one is big. It's right near the surface, and it has the radius right underneath, making like a little hard table. So this is a really good one to take someone's pulse from, because again, it's kind of throbbing right under the surface, and it's got something hard right behind it that you can pin it against, so you can feel it. Like you trap it between your finger and the radius, and you can feel it pushing in there. So the radial artery is one of the ones we usually use, like you're taking somebody's pulse. That big artery right near their thumb. The ulnar artery is a little deeper and doesn't have the same situation to make it easy to pin, so it's hard to really feel. If we are looking at the pulse on their finger here, so again, we're going to have our pulse transducer here. And anastomosis, I should give you a definition. Anastomosis. I cannot freaking spell here. Hold on. This is when there are multiple paths to the same place. So instead of just there's only one blood vessel to get from point A to point B, this is what's called an arterial anastomosis right here. If you are here and you want to get to the finger, you can go this way or you can go this way. Either one's going to get you where you're going. It's not as common in the arteries. In veins anastomose like crazy. But there are some important cases of arterial anastomoses. One is right here. Another one's the circle of Willis, feeding your brain between the vertebral arteries and the carotid arteries. So in this last part of the lab, we're just kind of showing what happens, or demonstrating this by putting if you just blocked one of these arteries, what's going to happen to the pulse at the finger? Is the pulse going to disappear?
No.
No, because the blood can come through the other direction. If I block just the radial artery, is the pulse going to disappear?
No.
Nope, because I can go the other direction. What happens if I block both of them?
Pulse will disappear.
It's probably pulse is going to disappear. Now nothing's getting there. What if somebody just cut their fingers off on a bandsaw and I just want one place to push to keep the blood from flowing down and just spewing out of their fingertips? Where could I push to just stop the blood from going down to their hand? The majority of the blood.
Brachial artery?
Yeah, I could just push right here. Right, this is an important pressure point to know about. One is you can feel the pulse. You're actually going to need to find the brachial artery when we're doing blood pressure later on. But it's also good to know as a kind of one spot to push to keep the majority of the blood from coming down into their lower arm in case there's some horrible injury. So the next little video I'm going to show you is the video of somebody pushing on those and see how it affects the pulse. So it's part 3.
All right, so now she's taken off.
Right. Now we're just looking at pulse. We don't care about EKG anymore.
Just has the pulse transducer.
Okay, so then I'm gonna start this.
Start this.
I'm gonna pull this down, make it a little bit bigger.
Okay.
Start.
All right, you can actually increase the magnification a little bit on there. Okay, so we have a nice pulse.
Okay, so
And-
now it's your
It's my brachial.
brachial. Yeah.
Okay.
So there you go.
Nice.
See that one spot?
Arm pressure.
The whole thing disappears.
All right, so now take that off.
Okay. Here we go.
All right, and it's coming back.
And then show her without it, her hand there anymore. Okay.
All right, now go on to your radial. It's down,
Nice.
but it's still there.
Whoa.
Oh, whoa. All right, go on to your ulnar. So you have the majority of it coming through your radial.
Interesting. Yeah, that was interesting.
All right,
Right, so you saw that, like, it went down. If it only could go one path or the other, there was less of the pulse wave making it through, less amplitude there, but it didn't disappear.
so now you're gonna put it on both. Whoop. Ready? There we go.
Nice.
Nice.
Right, so there we see her. She's got fingers
All
on
right,
both.
and then
It's hard. I kind of went. I should have lingered on her fingers there, but she's got one finger on the ulnar, one on the radial, and again, it disappeared totally again. So just to kind of, it's just following what we were just talking about.
and beautiful.
Oh, yeah.
Okay, for this part 3, we have actually little things, regular pulse, what it looks like with a regular pulse. So you can have that. Oh, come on, silly goose. We have one blocking the ulnar, one blocking the radial, one blocking both the radial and the ulnar, and one blocking the brachial. So you can use that. They'll show up. There it is. There's like blocking the ulnar compared to, here's the regular pulse up here. Here we can see blocking the radial, blocking both the radial and the ulnar, flat line. Blocking blocking the brachial should also be, flat. So you can use these images to, flesh out your write-up about what's happening here. So are there any questions about this EKG lab? There's 3 parts to it. I think I was as clear as possible in saying like kind of what you should write up in there. Everything you need, the information is in there. I'm trying to, oh, you know what I didn't, okay. Hold on a sec. Oh, so palpating superficial pulse points. Should we have enough time? We should probably just do this now so we have time. So palpating superficial pulse points, in addition to being fun to say, is basically palpation is using your sense of feeling. What does it feel like? And there are a variety of pulses people take. One is just sometimes just to get somebody's pulse rate. How fast is their pulse right now? but it's also valuable for getting a sense of, do you have adequate blood flow to that particular limb? You can actually feel these different, like your dorsal pedis artery going into your foot or something, making sure that there's enough of a pulse, knowing that there's adequate blood flow going down. So these, and in different kinds of medical traditions and traditional Chinese medicine, like pulse diagnosis is huge. Like just from feeling the pulse, people can tell a lot about what's going on in your body. In the pulse, when you feel the pulse rate, how fast it's going, is just one of the many things that you can detect. You can detect how fast is it going. You can detect how strong is it. Is it really strong or is it weak? But then it's even beyond that. Like how is it more impulsive? Is it going ooh, 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 or is it more kind of soft, like wah, wah, wah? So there's all the people who are good at like working with pulses can detect all sorts of different qualities of the pulse beyond just, is it strong or weak, is it fast or slow. They can also tell, like, again, kind of more the shape. They talk about it being thready or this or that. So just kind of, we're not going to go into all of that, but just putting it out there that there's more to the pulse than just how fast is it going. And it is, let me go back.
So are we doing the EKG lab then and the heart sounds and pulse lab?
Yeah, that's what it says on your schedule for today.
Okay, yeah, I just wasn't sure because, yeah.
Yeah. Partly I was leaving it open depending on the timing, but we have time right now. So I think this will be kind of fun. What I'm going to do here, like, let's do the second part, do part 2 first, because that way we know for sure we're not going to run out of time. So right now we're doing part 2 of the heart sounds and pulses. And basically it's going to be palpating superficial pulse points. This is something where what I want you to do in your lab book, for each of these arteries, you want to try to find them and then describe them. Like, did you find it at all? If you found it, was it weak or strong? Was it easy to find? Was it tricky? We're going to do this in groups, so you can talk amongst yourselves. Like, I'm not finding it. We'll go up or down a little bit or whatever. Temporal artery, that's where it sounds like on the temple. Common carotid, that's a really normal one that takes someone pulse. It's on the side of your neck. It's the main artery supplying your brain and your head. So you should be able to feel that one really easy. Facial artery, that one's a little trickier. It's right near the angle of the jaw, but you should be able to feel it. That one, as long as you spend a little bit of time, follow the instructions, you should be able to find it. Brachial artery, that one is also pretty easy to find once you know where to look. It's more medial. So antecubital fossa, it's like in this little pocket of your elbow, inside of your elbow, but you want to kind of feel more medial to really notice it. And you have to kind of push in there. Once you find it, you'll feel it there. I feel mine pulsing in there, but you should be able to find that. Radial artery, that's the front of your wrist on the thumb side. That one is totally easy to find. That's the one that you've always used. Femoral artery, that one's in the groin there. That one is another good pulse point to know if you're trying to stop bleeding down to the lower extremity. Popliteal on the back of the knee, that one can be tricky. And dorsal pedis and tibial, again, those you You might or might not feel them. You probably will, but if you don't feel like a failure. Some of these are trickier to find and are weaker. And again, this is more fun usually when you have lab partners and you can try to find them and kind of, but you can also find these on yourself. When you're finding them on yourself, and if you have somebody in the room with you who wants to play along, you can also like have them be your subject right now. But don't use your thumb. Your thumb has a strong enough pulse of its own that sometimes if you're pushing on something, particularly if it's subtle, you might actually feel a pulse, but it's like your own thumb's pulse feeling its own pulse rather than feeling some other pulse. So as a rule of thumb, the rule of thumb is don't use your thumb to take a pulse. So what I would like people to do now, if you have your lab notebook, your lab manual there, this is on page 167 of your lab manual. Let's go off into Zoom land for 15 minutes. I'm going to put you all in breakout rooms and work with each other and see if you kind of have the same experience. And use a pen and just write down, like while you're doing it, write down what you observe. Like if you just do it and then like later like try to remember what did you find, that's not good. Just write down while you're doing it what you're experiencing. And it doesn't have to be much. It can just be like really easy to find, strong, something like that. But some actual description of what you or really tried but not sure I ever found it. So here we go. And we'll come back a little before the end and we can share what we find. And go. All right. So which were the ones that were like easiest?
Radio.
I mean, it's not a big surprise that the radial is one of the most common places to take somebody's pulse from.
The carotid.
Carotid as well. And again, what kind of things are going to make it easier to feel a pulse someplace?
How superficial it is.
Yeah, part of it's going to be how superficial, close to the surface. Like your aorta is a huge garden hose, but it's really deep. You're not really going to feel the aorta because it's really deep. It's not close to the surface. What other kinds of things are going to make it easier to feel a pulse someplace?
The size of the artery.
Yeah, if it's larger, there's more of a chance it's going to have pressure changes and volume changes you're going to feel. How about what other kinds of things maybe?
Would there be because I noticed that overall there was like it was harder to find the ones in the legs. Is it because it's like further from the heart, so they're not as strong?
I think it has. I mean, it could be partly that, but I think it's probably more just about there these other qualities we're going to talk about: the size, the depth, and also just like I was mentioning, like with the radial artery, like if you have something pulsing and you put your finger on top, it could just be running away from you. It matters as well also what's underneath it, whether you can kind of pin it down against something hard behind it. Again, if you remember from anatomy, if you've taken anatomy, the head of the radius is this, or the distal end of the radius is this big flat triangle that's kind of totally is a little platform to pin the radial artery against there. So, so
Also,
things like that make a difference. Sorry, what was that?
I was going to say I also think it depends on like palpation because I find like with the temporal one, if you press too hard, you lost it
Yeah, no, so you have
against the
to be,
bone.
yeah, you have to be for those lighter ones, you've got to have a bit of a subtle touch. Yeah, absolutely. But how strong the pulse, if it's a large superficial artery with something hard behind it, that's kind of a nice recipe to really like feel this thing thumping. And like I said, knowing where those pulses are can be practical as well if you're trying to stop someone from hemorrhaging, like knowing where the brachial artery is and knowing where the femoral artery is. Those are places where you can push and, kind of stop the majority of the blood flow to one of your extremities. So, for the last part of the lab, normally we would have stethoscopes and you would get to put on the stethoscope, and we're not going to be doing a lot of that. But what we do have, there's like a little YouTube video here, which, you should watch. It basically kind of talks about what the sounds are like and what generates them, which I already mentioned, right? When systole begins, as the ventricles squeeze, in fact, we can,
It makes a lub-dub sound.
right? When the
The
gosh darn it. Trying to,
first hearts.
wait, come on. Oh, there. So like when the ventricle is squeezing here and we want the blood to go out the aorta or the pulmonary trunk, we want to make sure that the blood doesn't go back up into the atria. Then these AV valves slam shut. That's going to be that first sound, the lup sound.
Sound lub, also known as S1, is caused by the closing of the AV valves after the atria have pumped blood into the ventricles. The second heart sound, dub, or S2, originates from the closing of the aortic and pulmonary valves right after the ventricles have ejected the blood. The time interval between S1 and S2 is when the ventricles contract, called systole. The interval between S2 and the next S1 is when the ventricles relax and are filled with blood, called diastole. Diastole is longer than systole, hence the lub-dub, lub-dub, lub-dub. Heart sounds are auscultated at 4 different sites on the chest wall, which correspond to the location of blood flow as it passes through.
So she actually said something that was weird. That isn't actually my understanding. The second sound is not from the AV valves, it's from the semilunar valves. So I need to go look at this again. It is important to notice, though, that diastole is longer, right? The refilling lasts a while, and then you get this looped up as you push the blood out, and then wait a while. So basically, there's a little quiz that you should all do. It's like 3 questions. It's going to take you it'll take you about like 60 seconds. But I would like you to do this before you're just kind of, all this is in your mind still. It's just basically what are the heart sounds from, and what did you find when you were checking your pulses? It's just like it's a really simple little thing. It's basically asking about diastole and looked up, and then also which vessel did you find had the strongest and faintest pulse, and you're done. So it's just a way to kind of wrap things up here and make sure you've thought about like what is the sound when you're listening to a heart. Again, I'm sure later on in your training you are going to, if you haven't already, you'll spend a lot of time with stethoscopes and really listening to real heart sounds and all that. But obviously, even if we were on campus, we couldn't do it because we'd be touching each other and getting too close to each other and wouldn't be able to maintain distancing. So it's just like a tricky time to try to teach this stuff right now. So are there questions about this? It's one of these things where I think you'll come out of the class knowing what you need to know. It just won't be as much fun as actually sticking electrodes on your partner and putting a stethoscope and listening to their heart thumping. But you'll still come out with the core theoretical understanding that you'll need as you continue on when you actually do get to be more hands-on. So that is Tuesday, April 13th, Human Physiology 2021. So
Quiz posted?
what's that?
Is that quiz posted? I was just looking for it and I couldn't find it.
Oh, let me double check. Perhaps it is not.
I was looking for it. It's not there.
As they say, oh, let me. Okay. Oh, why? Look, it's not posted. Okay, it is now posted. It should, oh no, now the whole unit. Okay, you are now online. Even though this looks like, oh my God, lab 15, it's another lab. You've done it already in like a little bit of time, just with hopefully having fun catching up with your friends. You just have to kind of record a little bit about what happened. So otherwise, that is it for today. And on Thursday, we'll get deeper into blood pressure. More about that cardiac cycle, the idea of stroke volume and what affects that. And ultimately, it's all going to be in service of understanding how the body controls blood pressure. So we got lots more to talk about the cardiovascular system, but we've already bit off quite a bit already today. So I will see you all. I'll be here for office hours, but otherwise, I'm officially done here.